Isabel Andrade, and this is my lab report 3 on black holes. For this report, I will provide an introduction covering the fundamental principles of physics used throughout this lab. I will cover the first part of the lab, which focuses on the mass of a black hole. Then I will cover the second part, which is a scenario-based concentrating on the black hole, a planet, and a spaceship. And lastly, I will conclude this report through some what-if questions. The purpose of the first part of this lab is to find the mass of a black hole using a computational model, GlowScript, that simulates interaction between a star of known mass and a black hole. By collecting the parallel and perpendicular measurements and net force, we're able to calculate the mass of the black hole. The purpose of the second part of this lab is through using a computational model similar to the previous one to find the initial velocity needed for a spaceship to fly close to the black hole before escaping the black hole planet system, without the spaceship entering the black hole or hitting the planet. Through the second part of this lab, we focus on key formulas derived from Newton's second law and gravitational force. An overview of results from this lab includes the calculated mass of the black hole as 7.66 times 10 to the 33 kilograms. Then in part 2, the initial velocity of the spaceship was calculated to be the vector negative 3.087 times 10 to the 7, 0.22 times 10 to the 7, 0 meters per second. For this lab, we will be using Newton's second law of motion, which describes how a system changes its motion when it experiences a net force. Since we're assuming the only force acting on the star is the gravitational force from the black hole, we're able to manipulate Newton's second law to be that the net force is equal to the change in momentum of the star over the change in time. We also know that the total net force is equal to the parallel net force plus the perpendicular net force. And since force net is equal to dp over dr, we can substitute dp over dr in where it states force net. Then we can split it even further by multiplying the magnitude of dp over dr by the directions. For this lab, we will also be using gravitational force. For this force, the formula states that force gravitational is equal to the constant g multiplied by the mass of the star and the mass of the black hole, all divided by the squared distance between them. By manipulating this equation, we are able to solve for the mass of the black hole. For the first part of the lab, here I have my code. My email is inputted so I get a unique calculated mass. The gravitational constant g is given, and the delta t is calculated to be 1 day in seconds. The first while loop is calculating the velocity of the stars in the x and y directions. In the second while loop, the velocities are calculated using the velocities previously done. I then change the initial and final momentums to the mass of the star times their respective velocities. Using all the previous calculations, the difference between final and initial velocity and momentum is calculated to find delta v and delta p. Now using these two calculations, we can calculate dp dt by dividing delta p by delta t. We know that a derived version of the momentum principle is that force is equal to dp dt, so that we can just set them equal to each other. Then, to calculate dp dt in the parallel direction, we need to write the direction of the momentum, or p hat, in the magnitude of the parallel, which is the final momentum minus the initial, over delta t. Multiplying these two values together, we get dp dt in the parallel direction. Again, we can set the dp dt parallel equal to f net parallel. To find f net perp, we know that f net is equal to f net parallel plus f net perpendicular. So to save some work, we can write dp dt perp as dp dt minus dp dt parallel. Once more, we set f net perp to dp dt perp. Then deriving the gravitational formula, we can solve for the mass of the black hole, finally. Finally, we are given a long list of varying masses for the black hole, so I took an average of these in Excel and I got an average mass of 7.66 times 10 to the 33 kilograms. For the second part of the lab, we are attempting to have a spaceship approach a black hole from an orbiting planet and then leave the system. This part focuses a lot more on the gravitational force equation. So looking into my code, I first entered the mass of the black hole that we previously calculated. The mass of the planet and the mass of the ship are both given, and the only other thing I changed was the velocity of the ship. I calculated this through trial and error, trying to find what values were able to get me closest to the black hole without crashing or without getting sucked in. Now, in the while loop, we want to find the force on the planet and on the spaceship. The two forces on the planet are from the black hole and the ship. So the planet's position minus the position of the object gives the value of r. I then extracted the magnitudes of the r values. I then created one last variable for the direction, which is the distance divided by the magnitude. Then plugging in the respective masses, magnitudes, and r hat, vectors to the gravitational force equation, I could get the force of the black hole on the planet and the ship, and added them together to get force net on the planet. I then did this exact same process for the forces from the black hole on the ship and planet on the ship. I then used Newton's second position update formula to update the velocity and position of both the planet and the ship. Here is the result of the code. The planet in Chiron orbits in a circle, and the ship of the magenta heads towards a black hole and then escapes, leaving the system. So, how is the net force and its parallel and perpendicular components different from the change in momentum and its parallel and perpendicular components? Well, mathematically, they're equivalent. The biggest difference is that the rate of change in momentum is something we can do through direct observations of the object's position, velocity, and momentum as a function of time, whereas the net force is not something we can calculate without knowing the mass of the object. In order to have the spaceship orbit the black hole instead of enter and leave the system, I would have to change the initial velocity. I did so by changing the total time to 3 hours instead of 1, and then I found the velocities to be -1 times 10 to the 5th meters per second in the x direction and 7.75 times 10 to the 6th meters per second in the y direction, which was calculated through trial and error.